Hi everyone, I'm Julia, the chemistry tutor, and today I'm going to talk about solutions. And I'm going to talk about the concentration units that are involved with solutions. So let's get started. So way early on in your chemistry learning, you learned that solutions are mixtures, right? It's got more than one thing in it. It's got two or more things in it. And for a solution, we have a solute plus a solvent is what makes your solution. Okay, and your solute is the chemical that is mentioned. The solvent is usually water in general chemistry classes, right? And so your solution is your solute and your solvent. Okay, so if I put like sodium chloride into water, I would have a solution of sodium chloride, a sodium chloride solution. It would no longer be water, and it would no longer be sodium chloride. It would be a mixture, a solution of sodium and chloride. Okay, generally, what we say is the solute is the one in the lesser amount, and the solvent is the one in the larger amount. Okay, so if I said that I put 25 grams of sodium chloride into 500 grams of water, I would have those together. I would have 525 grams of solution. Okay, so you have to add them together to get your total amount of solution. And in that solution, because we said we look at the smaller amount and the larger amount, this is your solute, this is your solvent. Okay, if I had put that the other way or a different way and said that I put 50 grams of sodium chloride into 25 grams of water, now in this case, this is your solute because it's the smaller amount. This is your solvent. Okay, but generally, water is your solvent and your chemical is your solute. Okay, so in general, you put a solute into a solvent and you make a solution. The solute is the smaller amount, the solvent is the larger amount, and you add those together to get your total amount of solution. Okay, so there are a few units that we use, a few concentration units, and one of them we have a mass percent. One is a mass volume percent. Oh, I'm going to do this differently. I'm going to do my volume first. A volume percent and a mass volume percent. Okay. All of these, because they are solutions, are your solute over solution times 100 to get your percent on there. Solute over solution times 100%. Solute over solution times 100%. Okay, so they're all the exact same thing. The only difference is your units. If you're mass, this is grams of solute, grams of solution. If you're volume, for solutions, volumes are in milliliters. So your milliliters of solute over milliliters of solution. If you're mass volume, grams of solute, milliliters of solution. Okay, so the only difference in those three concentration units are your grams, milliliters, grams, milliliters. Everything else is always the same. The solute over solution times 100%. Okay, so for example, if this one that I had up here, I had put 25 grams of sodium chloride, so that's my solute, and these are both in grams. So we're doing a mass percent. So my 25 grams of my sodium chloride into my, together, the two of them together, 525 grams of solution times 100%. Okay, if they tell you an amount of water, you are going to have to add it to your solute in order to get your total solution amount. Okay, if you had said 25 grams of sodium chloride over 500 grams of water, that is not the correct calculation because the bottom is solution, not solvent. Okay, so your solution is everything that's there, your solute plus your solvent. Okay, so you can calculate it by just putting your mass of your solute over your mass of your solvent times 100, or volumes, or mass and volume. Okay, if you are given a percent, so if you're asked for percent, just plug your info into the equation. Okay. Okay, but if you are given a percent, it is a conversion factor. Okay. So if we are given the percent, do you agree with me? If I had a 25%, I'm going to say by mass, so that's mass of potassium hydroxide solution. Okay, do you agree with me that 25% means 25 over 100? Because it is by mass, that is grams and grams. The top is your chemical, the bottom is your solution. So there's our conversion factor from that. But remember, a solution, this solution has potassium hydroxide, water, and your solution. So I just related potassium hydroxide and solution. What if I want to know how much water is in there? Well, if I have 100 grams of solution and 25 of it is potassium hydroxide, the rest of it is water. Okay, so my 100 minus my 25, I have 75 grams of water. This came from 100 grams of solution minus 25 grams of solute gave me my 75 grams of solvent. Okay, so that one right there just related water and solution. So what if I wanted a relationship between water and potassium hydroxide? Okay, a relationship between water and potassium hydroxide is going to be those two. So in 100 grams of solution, I have 25 grams of potassium hydroxide for every 75 grams of water. Okay, so here I related my solute to my solvent. Okay, so every percent gives you 3 conversion factors: your solute to solution, your solvent to solution, and your solute to your solvent. Okay, so up here I said if they give you an amount of water, right, given that amount of water, you have to add. So given an amount of water, you have to add it. Okay, down here it's if you're asked for water, you have to subtract it. You have to do subtraction. Oh, I'm spelling that wrong. Okay, up here is adding your solute plus your solvent to get the solution. Down here is taking your solution minus your solute to get your solvent. Okay, so if you just think about that, like I had written it earlier, solute plus solution plus solvent gives me the solution. If I want to solve for solvent, I would subtract off solute. And that's what we just did right here, our solution minus our solute to get our solvent, okay? So that's our percentages. So I'm going to switch over to another screen and we're going to do a little practice with that. I forgot to mention a minute ago, mass, we could say by mass. Volume, we could say by volume. And mass volume, we would always say mass volume, or we would say MV. This could be MM, and this could be VV. Okay, so by mass or MM means mass percent. By volume or VV means volume percent. And M over V means mass volume percent. Okay? Okay, so now we're going to pop over to that other screen. Okay, so let's do a couple of problems with this. So this is asking me, oh, hold on, sorry. Okay, so this one is asking me, what is the mass percent? So we know automatically we want to know how many grams of our solute, sodium hydroxide, over our grams of solution times 100%. Because they're asking for the mass, we're just going to plug it into the equation. So we have 5 grams of sodium hydroxide and 750 grams of water. Okay, so this is our solute. This is our solvent. So we have to add those together to get our solution, correct? So our 750 grams of solvent plus our 5 grams of our sodium hydroxide, our solute, gives us our 755 grams of solution. Okay, so we put our solute, our 5 grams, over our 755 grams of solution times 100%. And when I calculate that, I get 0.66225 and some other numbers. And I've got 2 sig figs here and 4 sig figs here. So we're going to go with 2 sig figs in our answer. So 0.66%, and we could say by mass. Or we could just say percent. Okay, because you know it's by mass. So I made an error on that one. I did not pay attention to my sig figs. I lost a 0 in there. So this should have been 5.00 grams. This should have been 5.00 grams, and we're limited to the 1 decimal place there. And so this would now be 3 sig figs. Said 0.662%. And I know that feels weird. You're used to percentages having 2 decimal places, but they're going to have whatever your sig figs are. That's what you're going to be. Okay, so don't go by what you think it should be. Go by what your sig figs actually are. Okay, so now this next one is asking us for a mass of sodium chloride. So we want to know how many grams of sodium chloride. We've been given some kilograms, and we've been given a percent. Remember, percentages are conversion factors. So that means 2.50 over 100 is by mass. So that's grams and grams. My solvent, my solute is potassium chloride, and my bottom is solution. So there's my conversion factor. So this 1.250 kilograms is the only number that is not a conversion factor. So 1.250 kilograms, and that is of your solution. Okay. It is vitally important when we are doing percentages to absolutely say, are we talking about our solvent, our solute, or our solution? That is vitally important. Okay. So we have kilograms of solution, and our conversion factor has grams of solution. So first, we need to convert this kilograms over to grams. And now we can use our conversion factor that 100 grams of solution is the 2.50 grams of potassium chloride. And we are left with grams of potassium chloride, which is what we're looking for. And if you do that math, you get 31.3 grams of potassium chloride. Okay. So the first one asked us for a percent. We put our solute over our solution times 100. The second one gave us a percent, so we used it as a conversion factor. Okay, so now this one is asking us how much water is in, and all of this is giving me volumes. So that means how much water means how many milliliters of water, because we're talking about percentages. And remember, percentages are in milliliters for volume. Okay, so we've been given this percent. So we know that means 6.75 over 100. Since it's by volume, it's milliliters and milliliters. And the top is your chemical, your ethanol. And your bottom is your solution. Okay. So I'm going to start with a number that I have been given that is not a conversion factor. So that many milliliters of blah, 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 solution. Okay, so that is our solution. And I can go straight to my given conversion factor, the percentage. And, oh, but they asked for water, didn't they? Okay, so I messed that up. So we need water. Okay, so water, so if we have 100 milliliters of solution and we subtract off our solvent, our solute, we get our solvent. So I have 93.25, and this is, okay, so the 100 is an absolute number. So that's decimal places go on forever. So this subtraction, we're limited to the 2 decimal places. So we have 93.25 mils of water for every 100 mils of solution. Okay, and so if we do that math, we get 512.9 milliliters of water. Okay, because I've got 4 sig figs here and 4 sig figs here, and this is an absolute number. So I'm going to go with 4 sig figs in my answer. Okay, so see how I almost messed that one up? It was when I realized, because I wrote this up here. Okay, I always write my question down so I can go back and double check that that's what I'm doing, that I'm doing it correctly. Because that one asked for water, we had to do that subtraction over here to get our conversion factor, that 93.25 mils of water for every 100 mils of the solution. Okay. All right. So let's look at this one. So this one is asking us for grams of water. So again, it's asking for water. So we know we're going to have to do a subtraction. Okay, remember, if it gives you water, like up here, you have to add. Oh, that got all kinds of crazy up there. Okay, so we added that our solvent to our solute. So they gave us water, we added it. They ask for water, we do some subtraction. Okay, so we've been given a percent. We know that means 9.50 over 100. It doesn't say by mass, but it's grams. Grams is all they're talking about, so it has to be grams. The top is your chemical, your solute. The bottom is your solution. So my 4 grams of sodium hydroxide is the only number that's not a conversion factor. Okay, but they're asking for water, so we need to take our solution minus our solute and get our water. But this is asking about, okay, so this conversion factor is 90.50 grams of water for every 100 grams of solution. So our relationship is between water and sodium hydroxide. So our relationship is water and sodium hydroxide. So for every 9.50 grams of sodium hydroxide, I have 90.50 grams of water. There's my third conversion factor. So we can use that saying we know that there are 9.50 grams of sodium hydroxide on the bottom to cancel to my 90.50 grams of the water on the top. And if you do that math, you get 38.1 grams of water. Okay, because I had 3 sig figs here, and 4 here, and 3 here, so 3 in my answer. Okay. So both of those, they were asking for water. We had to come up with the other conversion factor. We had to subtract solute from solution to get our water. And then number 4 there, I had to do the third conversion factor of solute to solvent. Okay, so now this one is asking what is the mass volume percent. So it's asking for percent. So we're just going to plug it into the equation, mass volume, and my solute is my chemical, and the bottom is my solution, times 100%. Okay, so I have 45 grams of my solute, over, enough water. So we have enough water. They didn't give us an amount of water, so we don't have to add it. That is our entire volume of the solution. So we have 500 milliliters of the solution times 100% to get our percent on there. Okay, and if you do that math, you should get 9.00%. Okay. I think I actually got exactly 9 in my calculator, but we know this is 3 sig figs, 4 sig figs, so we need 3 sig figs in our answer. Okay, 9 is only 1 sig fig, so put the decimal in the zeros. That gives it 3 sig figs. Okay, so on mass volume percentages, they are usually going to say enough water, because you can't add grams to milliliters. I could not add 45 grams to 500 milliliters because they're not in the same unit. That would be like adding feet plus gallons. That doesn't make any sense at all, does it? Okay, so if it's mixing the mass and the volume, they're usually going to say you have enough water and you know your solution. Otherwise, they would have to give you a density to get from grams to milliliters or milliliters to grams. Okay, so Typically mass volume, they'll give you your volume of solution. You don't have to add any water. Okay, so looking at number 6. Oh, number 6 is a different topic. Okay, so let's pop over here. Okay, so I just did all of your types of percentages, some problems, some example problems for all of your types of percentages. They're all solute over solution. They're all, the units are based upon the type it is, mass, mass, volume, 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 mass. If they ask for a percent, you just plug it in to that equation. If they give you a percent, you use it as a conversion factor, your number over 100, and it tells you what your units are by what type of percent it is. And if they ask for water, you will have to do a subtraction. If they give you water, you will have to do an addition. Okay, so now I'm going to talk about molarity. Is our other major unit that we use for concentrations. Okay, so molarity is abbreviated big M. It's a capital M. We could also call this molar concentration. Okay, it's the concentration in molarity. And its units are moles of your solute over liters of solution. Okay, and that can also be written moles of solute over 1,000 milliliters of solution, right? Because 1,000 milliliters and a liter are the exact same thing. So if the units that they're giving you are in milliliters, it's kind of handy to see that as 1,000 milliliters, because then you don't have to convert from liters to milliliters. Okay. Some of your instructors, most of your instructors are going to be okay with that. Some of them are going to require that you use liters and do that conversion. You'll just have to check with your instructor on that. Okay. So I can ask you something like, I can say, what is the molarity of 40 grams sodium iodide? Oh, no, I'm going to use a different chemical. Potassium iodide in 500 milliliters of solution. Okay, so our question is molarity, that is moles of our solute, which is our chemical, over liters of that solution. Okay, so it's not as vital with molarity that you worry about solute, solvent, and solution, because molarity doesn't really talk about the solvent at all. We are assuming the solvent is water. There is enough there to give us a total volume of solution. In molarity, we're not going to have to add and subtract water. Okay, so this is just that Ki solution. So we know we need our volume of solution on the bottom, right? Because this is volume. We want our volume on the bottom. So we find our volume. So we have the 500 mils of solution. And on the top is our solute. Okay. But we need it in moles per liter. We're in grams per milliliter. So first we need to convert our grams. Oh, Ki, I did change that chemical. We're going to have to convert our grams to moles. And remember, to convert from grams to moles, we're always using the molar mass off of the periodic table. And 1 potassium and 1 iodide weighs 166.00. On the bottom to cancel to 1 mole. So we're at moles on the top, which is what we want. Now we need to convert that milliliters into liters. Milliliters on the top to cancel over here. So that milliliters of solution on the top. It's the 1 liter of solution on the bottom. Those cancel, and I'm left with moles per liter, which is what I'm looking for. Okay, so when you are asked for the molarity, you just plug it in and convert whatever they give you, grams to moles, just get moles on top, liters on the bottom, and do the math. I do this, I get 4.819. I will go with 3 sig figs. I'd call that 4.82 molar. Okay. Okay, if you are given a percent, given a molarity, just like percent, it is a conversion factor. Okay, so if I say that you have 6.3 molar sodium sulfate, that means you have 6.3 moles of sodium sulfate per liter of that sodium sulfate solution. With molarity, we don't really put solution in a lot because we know it's a solution on the bottom. In molarity, it's always the liters of solution. For percentages, right, depending on what you're talking about, your 3 different conversion factors, the bottom is not always solution. Sometimes it's water, okay? But on molarity, because we never add and subtract the water or the solute or anything, I just say it's the chemical, liters of that chemical, okay? We can also call that 6.3 moles of sodium sulfate per 1,000 milliliters of sodium sulfate. Okay, it's the same exact thing. All right, so let's do a few practice problems with that. Okay, so the first practice problem is essentially exactly like the problem I just did as an example. Okay, so if we have city water contains roughly 28 grams of sodium chloride per 500 milliliters of the seawater. Okay, we want to know what is the molarity. So I want to know how many moles of sodium chloride per liter of that sodium chloride solution, the seawater solution. Okay, so I want my volume on the bottom. So our 500 milliliters of that sodium chloride solution on the bottom, 28 grams of the sodium chloride on the top. So we need to convert our grams of sodium chloride into moles. And if you add 1 sodium and 1 chloride, you would get 58.44. So 58.44 grams. And periodic table is always 1 mole. So I'm at moles on the top, which is what I want. So now I'm going to convert that milliliters into liters. My milliliters on the top over here to cancel. And my liters on the bottom. Those milliliters cancel, and you're left with moles per liter, which is what you're looking for. Okay, and if you do that math, you should get 0.958. I'm going to go with the 3 sig figs there because I've got 3 here, 4 here, 4 here, and that's an absolute for the 1,000. Okay, so 3 sig figs, so 0.958 molarity sodium chloride. Okay, and by the way, we can also call that molar, big M, molar or molarity. Okay, so now we're saying what is the molarity? So again, our question is moles per liter of a solution by 25 grams of sulfuric acid. So that's our solute. Enough water to make 350 mils of solution. Oh, started putting my number in my question. So this is my sulfuric acid solution. So we want our volume on the bottom. So we put our 350 mils of that solution on the bottom. So that means our grams is going to go on the top. Okay, so I'm going to ignore the bottom for now. I'm going to convert the top, my grams to moles using the molar mass. And sulfuric acid weighs 98.08 grams in 1 mole. We're at moles on the top, which is what we want. So now we're going to convert our milliliters into liters. The 1,000 milliliters on the top over here to the 1 liter on the bottom over here. Those cancel, and we're left with moles per liter, which is what we're looking for. And if you do that math, you get 0.728 molarity H2SO4. So now, how many grams of sodium chloride? Okay, so our question is grams of sodium chloride are contained in this volume of that molarity. So we were given a molarity that is a conversion factor. We know that that means 0.40 moles of that solution of, that solute over 1,000 milliliters of that solution. Okay, we could also say this as that many moles over 1 liter. Okay, those are the exact same thing. But since we're in milliliters here, I would use the milliliters, but I'm going to do it both ways to show you. You'll get the same answer. You just need an extra conversion factor if you use liters. Okay, so this is our only number that is not a conversion factor. So we're starting with the 50 milliliters of that sodium chloride. If I use my top conversion factor, I just put my milliliters on the bottom, my moles on the top. Okay. But it's asking for grams. So we need to get from moles to grams using the molar mass. And on your periodic table, if you add up a sodium and a chloride, it is 58.44. And you're left with grams of sodium chloride, which is what you're looking for. And if you do that math, you should get 1.2 because this is two sig figs, 3 and 4. So I'm going to go with 2 in my answer. I'd actually gotten 1.1688. So the 6 rounds it up. So 1.2 grams of sodium chloride. If you had done that with liters instead, what we would have had to have done, because this is in liters and that's milliliters, is first we would have converted to, converted over to liters. Now I'm going to use my 1 liter. I'm going to use my molarity, my conversion factor. And then I would use my molar mass. And the math is exactly the same, because basically what we're doing by using sorry about that. By using the conversion factor with the 1,000 in it, is we're just getting rid of that 1 liter and that 1 liter and turning that into one conversion factor. Okay, it's the same exact math. You're going to get the same exact answer. If your instructor requires you to see it as liters, you're just going to need to put in this extra conversion factor to get from liters to milliliters. Okay, fix that so I can see. Okay, so the next one is asking us how many grams of barium hydroxide, so our question is grams of barium hydroxide, are required to neutralize this volume of that molarity. Oh, well, look at that. Okay, so it's 2 different chemicals. Okay, so because they say barium hydroxide neutralized in phosphoric acid, we have to do a balanced equation. So that's our best bet, is once we realize it's a reaction, let's do a balanced equation first. Okay, so it's a base plus an acid. Remember, bases have hydroxides in the back, acids have hydrogens in the front. So they're going to switch partners, double replacement reaction. Barium hooks up with phosphate. H hooks up with OH. I need to make my formulas true. And to balance this thing, I need... All right. If you have struggle balancing that, go back and watch my videos on balancing or email me to set up a session to talk about how to do some balancing. Okay, so we have a balanced equation. Okay, so looking at our numbers up here, that big M, we know that that is a conversion factor. So over on the side, I'm going to write that down. So it's that many moles of sulfuric acid to 1,000 milliliters of sulfuric acid. Okay. So our 45.9 is the number that's not a conversion factor. So I'm going to start with it. And that is milliliters of the phosphoric acid. So we have two different chemicals. So we know we're going to have to cross that mole river. So we have to get to moles. Okay, remember when you're comparing two different chemicals, it's always crossing the mole river. So you always go to moles. Okay, and oh, I don't have that up here. Hold on, let me go grab that sheet. If you have watched my video on stoichiometry, you have seen the middle part of this map already. You already know your grams to moles to particles, over to moles, grams, particles, okay? So you already know the middle part of this map. Now, for molarity, we're just adding that on to our map as another way to get to moles. So on that question we're looking at right now, we have grams of barium hydroxide. Oh, no, we're asking for grams of barium hydroxide. That's our question. I'll go ahead and write it on the other side. It doesn't really matter which one you call A and which one you call B. So we're looking for grams of barium hydroxide. And we're starting at milliliters of phosphoric acid. So we need, from our volume, we need a molarity to get to moles. We're going to use our stoichiometry to get to the other moles, and then we're going to use a molar mass to get up to barium hydroxide. What we had been doing before in stoichiometry is we were typically going from grams, but then this is all exactly the same. Instead of going from grams to moles, now we're going from volume to moles. It's just another road on our map, just another way to get to moles. Okay, so to go back to that paper. Okay. So we are going from volume to grams, volume of one to grams of the other. To go from the volume, oh, something went weird here. Okay, so it's always the molarity. We have that molarity that they gave us. So 1,000 milliliters of that sulfuric acid to 1 liter, oh, phosphoric acid. Oh, I did all kinds of goof up on this. I didn't need to convert because I had already said milliliters here. Sorry about that. This is my molarity, 0.463 moles of phosphoric acid. Okay, so see how easy it is to get lost on this if you don't stop and really think about it and really look at that map. Okay, so I was already at milliliters, so I didn't need to convert. I didn't need to do a conversion of milliliters to liters. Okay, so I went straight to my given conversion factor, my given molarity up there. Okay, now I'm at moles. As soon as you get to moles is where you cross that mole river using your balanced equation. We know that we want phosphoric acid on the bottom to cancel and the barium hydroxide on the top because that's what we're looking for. And in our balanced equation, 3 barium hydroxide to 2 phosphoric acid. And now we've gotten to moles. And in order to get from moles to grams is our molar mass, right? On that map, we went from milliliters to moles using molarity, moles to moles using our stoichiometry, crossing that mole river. Now we're going to go up and go to grams using the molar mass. And 1 mole of barium hydroxide weighs 171.35 grams. And we're at grams, which is what we're looking for. So if you do that math, you would get 0.546 grams of barium hydroxide. Okay, so molarity is just another conversion factor. You can calculate the molarity given the information, just like we can calculate a percent given the information up here. But if you're given the percent, it's a conversion. If you're given the molarity, it is a conversion. Okay, so now there's one last thing to talk about with solutions. Oh, there is another one. It's called molality. I'm not going to go into that today. Its units are moles of your solute over kilograms of solution. Instead of liters, it's kilograms. And so that you're typically going to have to be given a density to get from volume to mass. Okay, we don't use this one very often. In general chemistry, uses it a couple of times. Allied health chemistry probably doesn't use it at all. So I'm not going to talk about molality. What I am going to talk about is dilutions. It's our last thing on this. Okay, so you have an equation for dilutions, and that is your first molarity times your first volume is going to be equal to your second molarity times your second volume. Or you could see it as your first concentration, first volume, second concentration, second volume. Because concentration can be either molarity or percent. It can actually be any concentration units you want it to be. Okay, and some instructors might call that M initial, V initial, M final, V final. They might call this M concentrated, V concentrated, M dilute, V dilute. Okay, because a dilution is you're just adding water to something to make it less concentrated. Okay, I'm typically going to go with the M1V1 equals M2V2. Okay, so when we're talking about that, you know that you are taking a chemical, so some chemical, you're adding water, and this is concentrated, and you are getting a dilute chemical. Okay, the same chemical. Okay, these never have two different chemicals in them. They are never a balanced equation. They are never a reaction. All you're doing is you're adding water to something to make it less concentrated. So for example, if you were making orange juice from those frozen cans of concentrate, okay, so to start out with, I would have concentrated would be my first molarity. My first volume would be 1 can. Okay, then when we add water to it, we add 3 cans of water. Okay, so on the end, on this side, you have dilute and 4 cans of stuff in it. Okay, so when you're looking at this, your M1 is always the higher concentration. And the V1 is the lower volume. Over here, your M2 is your lower concentration, right? Because you've diluted it, so it's a lower concentration. And because you've had to add water to do that, your V2 is the higher volume because you have more water in it. You've raised your volume. Okay, so that's how you can easily tell your M1 V1 from your M2 V2. M1 more concentrated, V1 more, less volume, M2 less concentrated, V2 more volume. Okay, so let's do some practice problems with that. Okay, and the way that you know this is you are given either 2 molarities and 1 volume, or 2 volumes and 1 molarity, and it's only 1 chemical and water. Okay. If you're given 2 chemicals, that is not a dilution problem. That is an entirely different type of problem. That's a chemical reaction happened. Okay, a dilution is specifically 1 chemical and you've added water to it. Okay, so I have 340 milliliters of a 5.5 molar solution. What will be the concentration if I add 560 mils of water to it? Okay, so we've been given 2 volumes and a molarity, and it's only 1 chemical. That is a dilution problem. So I'm going to go M1 V1 equals M2 V2. Okay, these are just like the percent problems, that if they give you an amount of water, you have to add it to your initial volume to get your final volume, right? Because your final volume is after the water has been added to everything. So over here, my first molarity, it's these two, right? Because if we look, this is a higher volume, but also if we add those together, it's a larger volume. So my first molarity is 0.50 molar. My first volume is 340 milliliters. My second molarity is what we're looking for, and my second volume is my 560 milliliters of water plus my 340 milliliters of my initial solution. Okay, so we get 900 milliliters of solution. Okay, and looking at sig figs there, okay, this is 2 sig figs and this is 2 sig figs, but we're doing addition subtraction here. So we're not looking at sig figs, we're looking at decimal places. 0 decimal places, 0 decimal places, 0 decimal places. So this number is 3 sig figs. It should have a decimal on that 900. Oh, I lost all of my numbers. There we are. Okay, so that second volume is 900 milliliters. Okay, and to do that math, we would just divide by the 900. I didn't do this like I have been doing most of my problems. If we have the M1 V1 equals M2 V2, and we're isolating for M2, V2 comes down to the other side. So I get M1 V1 over V2. Over M2. Oh, V2. We are solving for molarity. Okay, and so I have my first molarity, my first volume divided by my second volume. And if we do that math, we should get 0. Oh, that's not true. 0.19 molar. And if you look, that is a lower concentration than my first one. So my concentration went down, which it should have. That's probably good. Okay, so here, okay, so up in this one, they gave us water, gave an amount of water. So you had to add. Okay, this one here is asking us for how much water. We're going to have to subtract. Okay, so we've been given a volume and a concentration, and it's asking for how much water was added. After the water was added, here is our new concentration. Okay, so this is our lower concentration here. So that's our M2 or C2, concentration 2. Use M1V1, M2V2. So my second concentration was the 1.60%. My first concentration was 3.5%. And my first volume was 200 milliliters. So we're solving for that second volume. And that's typical when you're solving for water, solving for the second volume. Oh, sorry, I didn't put that in like I had been doing. I'm going to try and stay. We're isolating for V2. So M2 comes to the bottom on the other side. So M1 V1 over M2 equals that V2. So 200, my 1.6%. Okay, the percent signs cancel, and you're left with a volume, the milliliters, which is what you're looking for. Okay, and if I do that, I get 437.5 is my final volume. Okay, but to figure out how much water you added, you have to subtract off your initial volume. Okay, so my V2 minus my V1. Okay, remember I said we're asking for water, so we're going to have to do a subtraction. Okay, so 237.5 milliliters. Okay, and because that was all subtraction, this one here was technically 3 sig figs, 2 sig figs. So 2 sig figs, 4 sig figs, 2 sig figs. So this number is 2 sig figs. Okay, but we're doing addition subtraction, which means 0 decimal places. 0 decimal places. So we're going to go with 0 decimal places. The 5 rounds that up. So 238 milliliters of water was added. Okay. So on dilutions, when they're asking you for how much water you added, you are solving for your final volume and then taking your final volume minus your initial volume to get your amount of water. Okay, so we've only got a couple more here. All right, here's another one. Let's see, if I leave, I have that volume and that molarity. And you'll notice on these, on none of these did I put the chemical in, because we don't really care what the chemical is, right? It doesn't matter. It's only one chemical, and all we're doing is diluting it. Okay, so if I leave that sodium chloride solution uncovered on a windowsill and 150 mils of the solvent, the water, evaporates, what is the new concentration? Okay, so that's asked in a really roundabout way. Okay, so first of all, if 150 milliliters of the solvent evaporates, right, I'm losing an amount of water. So I'm losing 150 mils of water. So I had, so we're going to go M1V1, M2V2 again. Okay. So I had a 0.50 molar solution, and I had 750 milliliters of it. If I let 150 milliliters evaporate, so that was my volume initial, minus my 150 milliliters of water, I had 600 milliliters left over, right? That's the volume after evaporation occurred. Okay, so we're looking for that molarity, and here's our second volume. Okay, so see how that's backwards of how I said your first volume will be the smaller one and your second volume the larger one? Well, because we're not adding water, we're evaporating water, we're not diluting, we're concentrating. It's the other direction, okay? But the big thing is because we talked about an amount of water, an amount of the solvent, we had to do a subtraction, okay? Because we asked about, right? We gave you an amount for that. Okay, so, no, I didn't rearrange that first. We're solving for M2, so V2 comes to the bottom. So that V2 is on the bottom. And that's going to equal my M2. And on that V2, the reason I'm putting the decimal at the end of that 600 is because I understand this is 2 sig figs and this is 2 sig figs. But when we do that subtraction, we're limited to 0 decimal places. So that number has 3 sig figs in it. Okay, and if I do that math, I get... Oh, no, I did not do that correctly. So here, let me... Okay, I get 0.625 molar. And the 5 is going to round the 2 up because now on our sig figs, we've got 2 here, 2 here, and 3 here. So we're going to go with 2 sig figs in our answer. So 0.63 molar. Okay. All right, so that one was a little bit different because instead of diluting, we're concentrating. Okay, so instead of adding water, we're removing water. Okay, so number 13 here. What was the concentration of 345 mils of a solution that was 250 molar after 155 mils of water was added to it? Okay, so because we're adding water, we're going to have to add, right? Okay. So, what was the concentration of 350 mils of solution after this much water was added? Okay. So, we initially had 345 milliliters. There's our V1. We're looking for that M1. What was the molarity? Okay, our second molarity is 2.50 molar. And the water that was added, our final volume, that's our initial volume, plus the amount of water that we added, gives us our final volume. So we had 500 mils as our final volume. Okay, so we are isolating for M1 here. So V2 moves to the bottom on the other side. So my V1 moves to the bottom on the other side. And I'm left with a molarity. And if we do that math, we get 3.6. And we are, let me write that whole number down. 3.62318 and some numbers. And we have 3 sig figs. This right here, addition was 0 decimal places. So that's 3 sig figs. And this is 3 sig figs. So I'm going to go with 3 in my answer. So 3.62 molar was the original concentration. And that is a larger concentration initial than my final concentration. So it's probably correct. So that is solutions. Okay, you have your percentages. Change my color here. You have your 3 percentages, your mass percent, your mass volume percent. Okay, they're all solute over solution times 100. It all just is all about what the units on those are. If you're given a percent, it is a conversion factor. And you have 3 different conversion factors: solute to solution, solvent to solution, and solute to solvent. If they ask for percent, you just plug it into that equation. You have molarity. Molarity is moles per liter or moles per 1,000 milliliters. They can ask for molarity, and you just convert to get moles in liters, or they can give you molarity, and it is a conversion factor. And dilutions, where you have one chemical, you're adding water, and you're getting a diluted of the same chemical. Okay, so you're given 2 molarities in a volume or 2 volumes in a molarity and only one chemical, and that is a dilution. And yeah, I think that is all I have to say about solutions and the concentration units for solutions. So have a great day.